2 days ago, at 18 hours, 56 minutes, and 58 seconds UTC, 168 seismic monitoring stations operated by the United States Geological Survey simultaneously detected something happening deep beneath the surface of the Atlantic Ocean. A magnitude 6.6 earthquake, shallow, just 10 kilometers below the seafloor. Yet where we so, on the central mid-Atlantic ridge. And the floor of the Atlantic Ocean moved. Not in the way the phrase is used loosely or metaphorically. It is literally, physically, geologically moved. 2 of the largest tectonic plates on the surface of this planet lurched further apart. New crust fractured and shifted, and the energy released in that single event was equivalent to approximately 480 megatons of TNT detonating simultaneously beneath the ocean. The Atlantic is on alert. The seismologists are watching. And the story of what just happened beneath that ocean and what it means for the living planet we inhabit is far more profound and far more important than a single earthquake data point can convey. Like and subscribe, because understanding what is happening on the floor of the Atlantic Ocean is understanding the engine that built the world you live in, and right now that engine just fired. To understand the full significance of what just happened, you need to understand the structure of the mid-Atlantic ridge itself. Because this is not just any underwater geological feature, this is the single most important geological boundary in the Atlantic Ocean, and arguably one of the most significant on the entire planet. The Mid-Atlantic Ridge is an enormous underwater mountain range that runs continuously down the center of the Atlantic Ocean floor, stretching from the Arctic Ocean all the way to the southern tip of Africa and beyond. It is part of the longest mountain range anywhere in the world, extending approximately 25,000 miles in total length when connected to the global mid-ocean ridge system. It runs like a spine through the heart of the Atlantic, dividing it in two, and it marks the precise boundary where 2 pairs of colossal tectonic plates are being pulled apart from each other in slow but relentless geological motion. In the northern Atlantic, the North American plate separates from the Eurasian plate along this ridge. In the southern Atlantic, the South American plate separates from the African plate, and it is at the southern junction of that second pair, between South America and Africa, at coordinates 0.5225 degrees south latitude and 20.015 degrees west longitude, that the magnitude 6.6 earthquake struck on June 17, 2026. Right at the heart of the zone where Africa and South America are pulling apart from each other, 1 centimeter at a time, every single year, year after year, for the past 180 million years. Like and subscribe, because what is happening at that boundary is one of the most extraordinary ongoing processes in all of Earth science. Let us put the scale of this geological boundary into a perspective that makes the magnitude of what you are dealing with genuinely comprehensible. Africa and South America were once joined. They were part of the same landmass, part of the ancient supercontinent known as Gondwana, sitting together on the surface of the early Earth approximately 180 million years ago. At some point, the forces operating deep inside the planet, the convection currents of the molten mantle flowing beneath the rigid crust, began to pull those 2 pieces of the puzzle apart. A rift opened between them. Magma from deep within the mantle began rising into that rift, cooling against the cold ocean water, solidifying into new oceanic crust, and pushing the 2 pieces outward in opposite directions. Africa moved east, South America moved west. The gap between them filled with new ocean floor, new rock, new seafloor geology manufactured from the interior of the Earth itself. And that process has been running continuously, without pause, for 180 million years. The Atlantic Ocean as we know it today, spanning over 5,000 kilometers at its widest point between South America and Africa, exists entirely because of that process. Every single square kilometer of Atlantic Ocean floor was manufactured at the mid-Atlantic ridge and then pushed outward toward the continental margins over geological time. The ocean itself is the product of the ridge. And the earthquake that just struck that ridge is a reminder that this process is not ancient history. It is happening right now, beneath the water, beneath the surface of the present, in the same geological instant in which we are living. Like and subscribe, because that is not a small thought. Now let us talk about the specific mechanics of what happened during this M6.6 event, because the physics of a mid-ocean ridge earthquake are distinct from what most people imagine when they think of the word earthquake. When you think of a devastating earthquake, you likely think of subduction zones, the places where one tectonic plate dives beneath another, grinding and locking and then releasing in catastrophic ruptures that can reach magnitude 9.0 and generate devastating tsunamis. The Sumatra earthquake of 2004, the Tohoku earthquake of 2011. Those are subduction zone earthquakes. And their destructive power comes from the enormous vertical displacement of the seafloor that they produce, which pushes massive columns of ocean water upward and generates the tsunami waves that travel across entire ocean basins. It is what seismologists call a normal faulting earthquake, a rupture driven by extension rather than compression. The plates are not grinding together, they are pulling apart. And when they pull apart, the crust fractures, blocks drop relative to each other along normal faults, and the energy of that fracturing radiates outward as seismic waves. The USGS confirmed no tsunami threat from this event and assigned a green alert level indicating minimal to no expected casualties or economic damage. But that absence of immediate destructive impact does not diminish the scientific significance of what this earthquake represents. The Atlantic floor moved, the plates shifted, new crust will form to fill the gap, and the Atlantic Ocean grew infinitesimally but measurably in the hours following this earthquake. The energy released in a magnitude 6.6 earthquake is worth examining in concrete terms, because the Richter scale and moment magnitude scale are logarithmic, which means that intuitive understanding of the numbers is genuinely difficult without unpacking them. A magnitude 6.6 earthquake releases approximately 2 times 10 to the power of 18 joules of energy. To put that in a frame of reference that means something, that is roughly 480 megatons of TNT equivalent, which is approximately 32,000 times the energy released by the atomic bomb dropped on Hiroshima. That energy radiated outward from the central mid-Atlantic ridge through the solid Earth, detected by 168 seismic stations operated by the USGS across the planet, recorded in the Global Seismic Monitoring Network, and processed by scientists into the data that confirmed what happened beneath those waves. The epicenter sat 1,031 kilometers northwest of Georgetown on Ascension Island and 1,022 kilometers southwest of Bonthé in Sierra Leone. It occurred at a depth of just 10 kilometers below the seafloor, which is shallow for a mid-ocean ridge context and is characteristic of the brittle upper oceanic crust, where magmatic stress and normal faulting mechanisms dominate. The rupture zone itself is estimated to have extended approximately 15 to 20 kilometers in length within that brittle upper crust. And when that rupture occurred, the seafloor on either side of the fault shifted. The Atlantic Ocean floor, the surface of one of the most dynamic geological systems on Earth, moved. Like and subscribe, because every number in that description represents a physical reality of staggering proportion. The broader seismic context of the Mid-Atlantic Ridge makes the June 17th event even more significant when you understand how this region has been behaving in the weeks and months surrounding it. The past week alone saw the strongest earthquake in or near the North Atlantic being this very magnitude 6.6 event. The past year in this seismic zone has been dominated by an extraordinary event that dwarfs even this recent earthquake in terms of raw magnitude. On February 9th, 2026, a magnitude 8.0 earthquake struck in this broader Atlantic region, which is an extraordinary figure by any measure. A magnitude 8.0 releases approximately 31.6 times more energy than a magnitude 7.0 and 1,000 times more energy than a magnitude 6.0. When you place the June 17th M6.6 earthquake within the context of that recent history of seismic activity in this basin, what emerges is a picture of an Atlantic Ocean floor that is dynamically, actively, continuously moving and responding to the tectonic forces operating within and beneath it. The Mid-Atlantic Ridge is not dormant. It is not quiet. It is one of the most seismically and volcanically active geological features on the face of the Earth. On average, the North Atlantic sees approximately 68,000 earthquakes per year. That is nearly 200 per day. The floor of the Atlantic is in constant, perpetual geological motion. What happened on June 17th was not an aberration. It was a particularly strong expression of a process that never stops. Like and subscribe, because the Earth beneath the ocean is never silent. Now let us address what makes the Mid-Atlantic Ridge not just a geological curiosity, but a system with direct, measurable consequences for the climate, the oceans, and the conditions on the surface of the planet where 8 billion human beings live. The Mid-Atlantic Ridge does not merely create new ocean floor. It directly influences one of the most critical systems governing the climate of the entire northern hemisphere. The Atlantic Meridional Overturning Circulation, known by the acronym AMOC, is the vast ocean circulation system that transports warm surface water northward, from the tropics toward the North Atlantic, and carries cold, dense, deep water southward back toward the equator. This system is the engine that keeps Western Europe remarkably warm relative to its latitude. London sits at approximately the same latitude as parts of Labrador and Canada, which experiences brutal Arctic-influenced winters. The reason London and Ireland and Scandinavia are habitable in the way they are, the reason the climate of Western Europe is so much milder than equivalent latitudes on the other side of the Atlantic, is AMOC. And the Mid-Atlantic Ridge plays a direct physical role in shaping how AMOC flows. The ridge acts as a physical barrier on the ocean floor that redirects deep ocean currents, influences how cold deep Waters move southward along the bottom of the ocean and affects the nutrient transport systems that underpin Atlantic marine productivity. When the floor of the Atlantic moves, it is not moving in isolation from the systems that operate above it. The geological and the oceanographic are intertwined in this ocean in ways that scientists are still working to fully quantify. Like and subscribe, because AMOC is already weakening at a historically alarming rate, and understanding the geological foundation beneath it is part of understanding the full picture of what is happening in the Atlantic right now. The Reykjanes Ridge, which is the northern segment of the mid-Atlantic ridge running southwest of Iceland, has been the subject of intense scientific attention in recent years, for reasons that extend far beyond routine earthquake monitoring. Scientists aboard the research vessel Meteor in June 2024, deep water basin along the Reykjanes Ridge, made unexpected discoveries about the volcanic and structural complexity of this portion of the ridge system. The seismic profiles they collected revealed terrain and internal structures that challenged existing models of how this section of the mid-ocean ridge system was behaving. Their findings were part of a growing body of research that ridge have shown capacity to turn suddenly disruptive, with eruption patterns and magmatic systems that do not conform to simple models. The ridge is not a uniform or predictable geological feature. It is a living system with regional variations, local complexities, and behaviors that continue to surprise the scientists who study it most closely. The M6.6 event on June 17th produced aftershock activity that is now being analyzed by seismologists at multiple institutions to understand what it tells them about the current state of stress and magmatic activity in this portion of the ridge. One of the most extraordinary pieces of scientific research published in 2026 adds yet another dimension to the story of what is happening in the deep structure of the Atlantic. In April of this year, findings published in the Seismic Record described the results of an unprecedented survey that processed 16 million seismograms from 4,700 earthquakes recorded at 25,000 stations across the planet. The research team generated 70,000 individual measurements covering 75% of Earth's deepest rock layer, nearly tripling the coverage previously examined at that level of detail. What they found at the base of the mantle, 2,900 kilometers below the surface, was the accumulated debris of ancient oceanic plates that had long ago subducted and sunk through the mantle over geological time. These dead plates, slabs of ancient ocean floor the size of entire continents, had reached the boundary between the rocky mantle and the molten iron outer core, where they buckle, fold, and spread sideways for hundreds of kilometers, deforming both themselves and the surrounding rock in ways that seismic waves can read. The significance of this research for understanding present-day plate behavior is profound. The mantle is not a simple, uniform medium through which plates float passively. It is a complex, three-dimensional environment shaped by the accumulated history of billions of years of plate movement, and the behavior of modern plates, like those on either side of the mid-Atlantic ridge, is directly influenced by the physical character of the mantle beneath them. The Atlantic floor that moved on June 17, 2026, is the surface expression of a system that extends all the way down to the core mantle boundary 2,900 kilometers below. Like and subscribe, because the depth of what is happening beneath that ocean is almost literally incomprehensible in human terms. The Atlantic Ocean itself, as a geological object, is the ongoing result of the mid-Atlantic ridge's activity over geological time. What is now Europe, Africa, and the Americas into the vast ocean it is today, spanning thousands of kilometers and containing an almost incalculable volume of water. The average spreading rate of the mid-Atlantic ridge is approximately 2.5 centimeters per year in the east-west direction. That rate sounds negligibly small until you apply it across 180 million years of continuous activity and realize that this process has produced an entire ocean. Every year, the Atlantic grows by about 2.5 centimeters. Every decade, 25 centimeters. Every century, 2.5 meters. Every million years, 25 kilometers. And in the 180 million years since Africa and South America began their separation, this process has produced an ocean that is now more than 5,000 kilometers wide at its broadest point. The earthquake on June 17th was one moment, one pulse, in that 180 million year process. And it is a process that will continue long after every human civilization that currently exists has come and gone. For those watching this and wondering what the immediate practical implications of this event are, the answer for the general public is reassuring in terms of direct hazard. No tsunami warning was issued. The USGS green alert level means no significant casualties or major economic damage is expected from the S-specific earthquake. The Mid-Atlantic Ridge is more than 1,000 kilometers from the nearest populated land areas, and the type of Fulton G involved produces far less effective tsunami-generating seafloor displacement than a subduction zone event of comparable magnitude would. But the scientific significance of this event, situated within the broader context of what we know about the Atlantic floor's dynamics, about AMOC, about the extraordinary pace at which climate is shifting the conditions of the ocean above this ridge system, and about the deep mantle processes that drive it all, makes this earthquake a moment worth understanding deeply, not just cataloging as another data point in a seismic log. The Atlantic Ocean floor moved on June 17, 2026. It was recorded by 168 seismic stations. It was analyzed by scientists at the USGS, at the German Research Center for Geosciences, at monitoring networks across the planet. It released energy equivalent to 480 megatons of TNT at a depth of 10 kilometers below the surface of an ocean that contains some of the most consequential geological and oceanographic systems on the surface of this planet. And it will happen again. The Mid-Atlantic Ridge does not rest. The convection currents in the mantle that have been pulling Africa and South America apart for 180 million years have not stopped. The magma chambers beneath the ridge that pressurize, rupture, and generate new ocean floor are not cooling. The engine is running, as it has been running since before the first dinosaur ever walked the Earth, and as it will continue to run long after the last human being has watched the last version of this video on whatever device or technology exists in the future that none of us can yet imagine. Stay with us, because this channel is dedicated to making the extraordinary dynamics of the planet you live on understandable, accessible, and genuinely awe-inspiring. Like and subscribe, and share this with anyone who has ever looked at the Atlantic Ocean and wondered what lies beneath it. Now you know a little more of the answer, and the answer is magnificent.